Okay, 14C is the section now. We're talking about exponential modeling. This will be revisited in more detail at the end of the chapter. So what are some key properties of exponential functions and why are they used for things like population growth? Well, if we have something like a to the x, this gets a times bigger when x increases by 1. So if we do a to the power of x plus 1, the law of indices says that this is the same as a times a to the x. And we saw this in the graph before. For example, when we had 2 to the power of x, we had y values like 1, and then 2, and then 4, and 8, and 16. So in other words, we multiplied by this number at the front when we moved to the right-hand side by 1 step. And you could go backwards with it as well if you wanted to the negatives to the left-hand side. What else do we need to know? So the rate of increase, so how much it increases, is proportional to the size of the population at a given moment. This is quite wordy. The best way to interpret this is that a coefficient at the front can multiply up or down the amount of change. So for example, if you have 2 to the x, okay, it means doubling, right? But if you have, say, a 4 there at the front, well, BIDMAS means that you will do that part there, and then whatever it is, it will get multiplied by 4. So if you have a number at the front, okay, that will, if we have a 4 there, it would multiply that increase, whatever it was, by 4, effectively. If you had 100 times 2 to the x, when you double, okay, you'll still double, but that will be multiplied by 100. So this sort of affects the amount that it would have changed as you increase the x value. Okay, so as you increase x by 1 here, you'll get a bigger change than if you increased x by 1 here. That's the idea, if x starts at the same value. An example, so the population in the Republic of Dave is modeled by this. So this means 100 multiplied by e to the 3t. So e to the 3t is the exponential part. That's where we'll start. And then we'll multiply by the 100 at the front. What's the initial population? So initial is a key word, and it means that the time is equal to 0. This does not mean that the population is 0 to begin with. It's very tempting to say that, but if we write this thing out and we substitute t in a 0, this becomes e to the 0. What is e to the 0? Well, it's actually 1. It's not 0, it's 1, isn't it? So 100 times 1, the initial population is 100. What this means is if you have a question where there's just like one part all multiplied together, the number at the front is often, but not always, okay? It's often the initial population. What's the initial rate of population growth? Rate means that something is changing with time. T is time. In other words, how does population change with respect to time? This is the language of differentiation. So when you talk about change and rate of growth and things like this, you're talking about differentiating. Remember that a to the ekt becomes ak to the ekt. That's what we said earlier. In other words, the 3 goes down and gets multiplied by the 100, so you get 300, and the e to the 3t part stays the same. It says initial again, so that also means t equals 0, so we get an answer of 300. So to start with, the population is changing by 300 at that particular moment, okay, when t equals 0. Another example there on the board, let's just have a look at this one together. So density of a pesticide is P, which is about density. T is time in days. We put this in bold because sometimes it's like days and weeks and you need to read it carefully, okay? Use this model to estimate the density after 15. In other words, this says, what is P when t equals 15? Well, that there is just a substitution, okay? If you substitute into the formula, you'll get your answer. Interpret the meaning of 160. We talked about this previously. 160 is what you would get when t is 0 in this case. So this must be the initial density. the initial density of pesticide in the field. Show that when you differentiate, you get Kp. P is that formula from before. It looks like just a letter, but it's actually all of that. So show that you get a number in front of all of this, where K is a constant. Okay, well, if we differentiate, we get Kp. If we differentiate, I mean, we certainly get this one here. I'm just thinking about the wording of the question here. The wording of the question is not very good. This should really say, show that we get Ke to the minus 0.06t. Okay, so there's a correction for that question. So what they want you to do is to differentiate and say the number that's in front of the E, basically. Okay, small mistake in the wording of the question there. Interpret the significance of the sign, the positive or the negative. Well, it's a negative. So what does that mean? And think about the context. Context is about pesticide. So what would the concentration of pesticide do over time? Well, you'd expect it to go down. So the density is increasing. The negative there means that the change is a reduction. So it's reducing. And because this is an exponential decay graph, we kind of expect that. Finally, sketch the graph of P against T. Notice here that we've only drawn the right-hand side because T is days afterwards. You're not going to have negative days, so it doesn't make sense. So we've only drawn the right-hand side. We've drawn an exponential decay graph, okay, and we've checked our y-intercept, which should be 160. That's why it looks that way. Okay, a couple more examples for you. So find the temperature as this thing enters the liquid. So as it enters, I mean, this is a T equals 0 question again. Notice in this context, it doesn't just have this part here. It also has a plus 25. So don't be tempted to just jump to saying 400 straight away. It's actually 425. You get 400 there, and you get 25. This is what the questions normally look like. They have the number E part and then plus or minus something. Find the rate. Well, what we would need to do for this one is we would need to differentiate. Okay, so you would need dt over dt because temperature and time. We differentiate this one. You'd pull minus 0.05 to the front, multiplied by 400. And then you would put this one here. Okay, the 25 will disappear, and then you need to sub in t equals 50. Okay. Another quick example. This here again only has one part. So pause the video, have a quick go at the questions. So assuming you've done that, the first two are substitution questions. What's the meaning of 12? 12 is going to be the initial number here. Show that after 6 months, the rabbit population is increasing by. So what does that sound like? Is increasing. This is the language of change. Change, we can differentiate for that one. Okay. After 6 months, so that means M needs to be 6, and you should get the answer. Finally, a very common part of the A-level that they love to do, and to get good at this, you need to just read the context and really understand what's going on. Suggest one reason why it will stop giving valid results. When values get very large, why would this model not work? Well, exponential growth in the long term can be unrealistic, okay? That's often a good idea to write down. In context, the rabbits may begin to run out of food or space. So there you go. Those are some reasons why exponential growth in the long term might be unrealistic. There are often many answers that you can give for limitations or critiques and things for a model. To be on the safe side, I would say something like exponential growth may not be realistic in the long term, as resources may become inadequate, such as food for the rabbits. Something like this, a mathematical and a contextual answer to make sure I get the marks. Right, that takes us to 14C. Some recommendations there from the book. We will come back to this later when we have more tools at our disposal.